So there are two methods. The
Mm-hmm.
lossless stuff where you just compress everything, and then there's so
Lossless.
like
Mm-hmm.
lossless, and then there's lossy.
Okay.
So with the lossless, you just like if you have something happening lots of times, you just try to encode it in a simple way, so you don't have to write that thing out lots of times.
Mm-hmm.
So you don't actually lose anything. And
Right.
yeah, they're like dictionary methods to do that. So it's like
Mm-hmm.
imagine you're going through a text and you see the word the a lot of
Yeah.
times, or you see the letter e a lot of times.
Mm-hmm.
Maybe you do it with words more, and then instead of writing the, you just put like a one, and
Okay.
so that saves a little space. And if every time you write, it's a
Mm-hmm.
bit like how instead of writing machine learning, lots of letters, you just write ML, or
Okay.
university, you could just do like a U or something. I don't know. You
Got
just
it.
do a short symbol, and then there's the lossy compression where so that's where the machine learning comes in. So you have to learn the patterns in the data, and so it's like hopefully you're going to remove the noise or
Mm-hmm.
stuff that's not necessary, and then keep the structure of the data. And then as you get to higher compression levels of the
Mm-hmm.
data, then you lose more of the structure. So it's a question of a balance between how much fidelity do you want in the signal and how much do you want to compress, which is more important. Got to get the balance right.
Mm-hmm.
And then you use things like principal component analysis and Fourier transforms. And then other things are very similar. So uh, cosine transforms is really similar to Fourier transforms. There's just no imaginary. And then there's the
Mm-hmm.
wavelets, which is so there's like a Haar wavelet, and you're trying to, if I can remember that. So okay, yeah. So the Haar wavelet's like I believe it is what I use. So you have so if it's a time series signal, right? You take the sum of two things next to each other. So like
Mm-hmm.
point one and point two, point two and point three, whatever. You take the
Mm-hmm.
sum of these, and that's one of your outputs, and then you take the difference, and that's another output. So it's almost like the first thing is the average of two signals, two
Okay. Okay.
timestamps, and
Mm-hmm.
then you can you can probably compress this by getting rid of the difference. So you just kind of take the average, and then you can actually do it multiple times in like a hierarchy, split it up again, and so you take the average, and then I think it is so that average signal or that sum signal really, it's kind of the same thing. Then you do it again, and you get another sum and another difference. And then if you delete we just zero out the differences,
Mm-hmm.
then in the time steps, then you're kind of getting rid of. Hopefully, it's like the high frequency signals, which is
Okay.
usually considered to be noise.
Mm, yeah, of course, which you don't want normally.
Yeah.
What could be some of the cases that this type of compression method does not work well? Or
Okay.
what type could be video, audio, documents?
I see. Yeah. So let me see. What I was working with was vehicle data and the various different signals there. So uh, okay. In theory, so it's just generally any type of data that varies a lot. You want to use more of the get rid of the high frequency stuff,
Mm-hmm.
and you can't really use like run length encoding, which is saying I see this word a lot of times, or I see that very signal a lot of times. So I'm just going to call it a one and say it's that thing again, rather
Right.
than writing it out. You can't really do that because it would actually make it bigger, so you
Mm-hmm.
wouldn't end up compressing it. So you want to kind of get rid of the high frequency stuff. So it's not necessarily you don't want to use it on a particular medium. but it depends what the signal looks like. So I know, like, probably, yeah, I think the best image compression is based on the what is called cosine, the cosine stuff,
Cosine
cosine
function.
transformations,
Okay.
cosine transforms. Yeah, I assume you're familiar with some of these things. Like, do you know Fourier transforms and PCA? Do you know about it?
PCA, you said?
Yeah.
Phase coefficient something, no?
Principal component analysis.
Okay, no, then I
Okay.
don't. Okay.
Okay, but do you know about Fourier transforms?
Yeah.
Okay,
Yeah,
sure.
I know
They're
the essence.
very widely used.
Mhm.
Yeah, it's like get rid of the high frequency stuff because it's probably noise. So that's
Correct,
what
yeah.
I'm doing a lot of times.
Mhm.
And then principal component analysis is like if you've got like imagine a scatter graph
Mhm.
and just do it in 2 dimensions. Like imagine the data kind of generally looks like that, kind of spreads out a little bit in that direction and a lot in that direction.
Right.
So most of the variance is in that direction. It's not in this axis and it's not in that axis.
Okay, neither in Y or X axis, but
It
it's
looks like that.
okay.
So why are you using these axes? Why not use these axes? Because then you just say it's more Y and a little bit of X, and they're always orthogonal. So you just rotate it, and then you kind of throw away anything less. So like if you have 100 different dimensions, you can throw away the bottom 97 dimensions, for example, because they don't add much variance.
Just by including that rotation of those axes and making it orthogonal, as you
So it's like it's rotating it, and then it's also saying, you know, we get most of the information from just these first axes, these new axes. Maybe I should move upstairs. And we don't
okay.
don't care about the rest of them because they don't add much. They add like the last 1% of information, all of those 97 axes. So don't talk about that.
Got it.
Hey, Peter,
That
you should probably do your
sounds
literacy.
Sounds interesting. Definitely.
Homeschooling. Hello, daughter. Un momento. Yeah, cool.
There we go. Yeah.
So
yeah, that sounds definitely interesting, and I believe there are many more kind of other methods to compress the data. Truly, I had heard before about lossy, but lossless. Actually, recently I heard of it, and I kind of didn't know much about this type of compression. And another maybe thing that I'll like to kind of maybe connect with another thing that I heard recently is that there was a guy was saying from, by the way, Comma AI in America. You might have heard this. It's another self-driving car company. Well, actually, they are building the software. You know, just like Tesla, but they are competing sort of in a sense to make the other cars that are existing normal petrol engines cars, turning them into, by of course installing in hardware like a mobile phone and with its camera and some other dongle device that can be connected to the OBD that turns your car into an autonomous car, of course, after installing the software. So that's Comma.ai in the US. And going to the point, the guy, it's called George Haas, it's also a known hacker, and he was saying that I heard that AI said it's no more than a lossless compression of information, and that was interesting to hear. I still don't
lossless.
truly
Yeah.
comprehend. I mean, yeah, how can you boil it down like that, or why it is exactly like that? But it kind of makes sense in the end, because
Yeah.
yeah, artificial intelligence, what we call a machine learning, I'll normally preferably say at these times, it's no more than mapping all the data towards the function or the output that we want to obtain, right? Taking all of those data input points, rearranging them accordingly to, or pardon, processing, not rearranging, but processing according to a specific neural network, and then adapting those data points to a given output. Might be, I don't know, a classification of fruits, orange, apple, or banana, or it could be even a yes or no. Is this, I don't know, you give it a question to the neural network and it will say, is it right, like, or wrong? I don't know, which object is heavier, whatever. A ball, for example, a football, or a stone, whatever. So yeah, backing up, that was interesting point, and I said, okay, good. It's good food for thought for myself, but still, I do not know the real details. How can AI be called or be like a lossless compression of information?
Okay. Yeah. So I've heard that before.
Mm-hmm.
Like that it's lossless compression. So when I totally agree with that, it's compression and machine learning are basically you need to learn the patterns in the data. But
Mm-hmm.
lossless compression, I sort of think it. I still think of it as lossy compression, where it's like, so take a lot of pictures of apples from different points of view and lots of different apples, and then you compress it down to what's important and forget about the rest. So the background isn't important, and it's
But
not so important that it's
sorry,
green or red. Or
how do you distinguish, Vincent, that, like, how would you specify that the background is not important? Will you have to still train this network to make the distinguish, well, to distinguish between the background and the object? How does the algorithm, well, in this case, the neural network, know that, well, that's not important to us, therefore I will omit that part, like the background, quote unquote, and that is important? Because imagine we might have, okay, I might have an apple here, but there might be another, I don't know, small apple on the background that is
okay,
difficult. I don't know, some edge cases, let's say. Aha.
yeah. So yeah, if you have like the simple classification, that image contains an apple, or if you have there's an apple there,
Mhm.
that's very different. So like if you and then even colorize, like I'm going to draw a picture, like a shape of an apple around the apple. I'm going to draw a shape of a car around the car. That's even better. So like,
Mhm.
they're higher levels. And so if it's going to do like there's an apple, then that's really good. But I guess it would. So I guess it'd use kernels for that. So like
Mhm.
look for apple at each point, and I don't care if it's zoomed in or pulled out,
Mhm.
turned to the side. And I guess you would train it to do that. Okay, with these kernels and the convolutions like CNN stuff, but you do that also by like varying the background. So having images from different sources and in different locations. So yeah, like I take a lot of pictures of apples and you take a lot of pictures of apples. Hopefully we can like put it one on the table, put it on a different table, put it on the grass. I don't know.
And then, yeah, you
Hopefully
make
we'll
it
get it.
more robust, right? I guess to detect those different scenarios where the apple would be maybe in different contexts.
Yeah.
Mhm.
So I really don't know. I've thought about that before, but I understand it better as it being lossy compression. So like you forget about the background. You only care that there's an apple there. I don't know
Mhm.
why some people say lossless compression. So you want to
Maybe
know the
because you
thing very well.
also, sorry if I interrupt, thinking, or I'm guessing, actually, I cannot say that I'm sure. Maybe because you will also carry the noises. You also encode the noises that's why it might be called lossless, because you don't lose either the important signal, but also the background noise, which admittedly it's almost everywhere actually. Of course, you may see a lot of noises from my side, meaning some blurry corners due to, I don't know, the camera chip or lens not performing 100% accurately, and other software issues of speed and so on.
Sure. Yeah.
And yeah, that would turn out to be noise, right? If you take a snip out of those, I don't know, 30 frames, you take one frame. But when you compress that complete frame without changing anything, without removing, well, applying a filter, removing the noise, that I guess might be called lossless. Whereas when you tend to perform some sort of pre-processing, or let's say using another neural network to pick what is the most important, let's say, feature on that picture, and then compress it, that might be lossy because we took only what we wanted and then we left out everything else. Well, this would be my guess, of course, but I'm not sure whether that makes sense.
So lossless, if you just, well, I sort of think the first thing was lossy as well, because like you just took one frame that was most important, or you cut out the frames that you don't like. Yeah, okay.
You take everything. You take everything, whether you deem the signal to be noise or a good signal, you will anyway compress it.
Okay.
Now, why you would do that, I'm not sure. Maybe this is another question, because I understand, to me makes sense. I like picking up stuff, meaning take what's useful and then throwing everything else out. And yeah, a question would be, why would you want to take everything in a picture, also the noise? For some reason, that could be perhaps to make some analysis, since noises may also be a source of understanding whether they are uniformly spread, and detect, or actually kind of analyze the way the picture was taken, whether it was modified or not, because we have the so-called GANs, general adversarial networks, if I'm not wrong.
I think they're generative.
Generative, pardon,
So,
yes. Generative.
well, you can make deep fakes with them. Yeah.
Correct.
Fake images. Yeah.
So in my mind, with GANs, you would want to have also the noise to have a good performance, instead of only the good signal and having thrown everything else, maybe, I don't know, the noisy background.
Okay. So you mean it's more realistic if we keep the noise?
Yeah.
You're trying to make a model of the real world.
Yeah.
Which is noisy.
Exactly. Yeah.
Okay. Okay. Yeah, from that point of view.
But then, of course, it's a trade-off, as most of things in life, right? Do we want to spend more computational power to process all that noise or not? So it depends, like in various settings and problems that we may face. But as I said, overall, I'm oftentimes a fan of just picking the data I want and leaving out everything else, because in that way we spend less computational power, and power equals energy, and of course we want to minimize that, so it's kind of a chain afterwards. But yeah, that was about an interesting thing that I heard. What else? Where do you see, I don't know, talking at this point now for the future, where do you see these things moving forward? Anything that you expect for 2021, a breakthrough or something in whatever field, I don't know, you may find interesting?
Yeah, I'm not sure. Yeah, I'm interested that, I think his timelines are usually wrong, but Elon Musk, he says he thinks machines are going to take over everything within 5 years. I think that's an extremely radical timeline. And he's usually wrong when he says, our company is going to do this in this year. it takes longer. So I don't know. That doesn't sound like one thing. That sounds like a whole lot.
Yeah.
But anyway, yeah. What do I think is going to happen this year? So, what recently? That was last year, but Google DeepMind, what they were doing this protein folding AI stuff, deep learning, and that was doing much better than anything before. They really got stuck into it, and they really used the powerful models, powerful methods to get really good models. So that was really good stuff. And I think everyone's researching in, like so many people are researching so much in healthcare and viruses, virology, communicable diseases, that sort of thing, epidemiology.
Yeah.
Lately. So yeah, making vaccines and everything. I think that's probably the thing that's going to advance fastest this year. Things to do with that. But what like specific technologies, I'm not sure. Like to support that.
Yeah, I understand. Definitely, it's difficult, Vincent, to predict. Even if you ask myself, okay, what would you think? What would be this year? The next thing? No, I cannot really say, but we may have a sense of what to expect. And actually, you well said. Pretty much what you said to me resonates, because I also I've heard what maybe starting with Musk has said about the singularity and predicting that we will have an artificial machine with the same computational power as our brain in 2026, or in 5 or 6 years, pretty much, roughly. And healthcare, yes, I also heard that, and it's obvious it's going to be a big, I think, not revolution, but breakthroughs in this field, especially at these times, because it's sort of, given the situation, it's a problem that we're currently living with, and of course we want to solve and use technology to solve more of it. You well said folding protein. That's, yeah, I heard as well, which was very interesting. Even though it might, for most of the people, when they might think of folding a protein, oh, where's the big deal or the problem with that? Well, if you think of those thousands or tens of thousands or even more variables that you need to model that folding protein, then you may understand the sheer complexity of. It's like trying to solve in parallel thousands of equations, and
yeah, sure.
and then represent that graphically, how the folding protein may look like. And even myself, I do not pretend to know actually exactly how they are done. I'm assuming that they might have 10,000 equations to model that, to create that model, but they might have even millions. I'm not sure. But
yeah,
healthcare, definitely agree. It's gonna, I think, this year, perhaps, or of course moving forward, we're gonna see some advancements into finding, for example, more cures. I also have heard about this. These guys working in longevity field or lifespan, because there are some guys that pretend now to also reverse the age, because they consider aging also as a disease now, not exactly as a natural cause, but even though it's not official in the sense that most these, who's that, like FDA, they do not want to claim that aging is a disease, right? But these guys working in that field, they say, well, we should treat aging as a disease, and for it we shall see in a couple of years actually having some cures or some treatments, be it CRISPR, for example. You might have heard about it, stem cells, gene therapies. So such methods, which truthfully I don't know exactly the details of each one of them, how they work, but in essence they would help us minimize, at least slow down the aging, because nevertheless it's not easy. In my mind, it's not easy. How can you slow down like aging? But they claim that they can slow down and even reverse at some point in time, given enough research in the
Okay.
medical fields. So that was also interesting and
Yeah.
what
So
to expect.
so the first name that comes to mind is Aubrey de Grey. Are you listening to him?
No, yeah,
He's
can
like a
you?
big gerontology guy.
No, I've. Can you read the? Well, say once more the name for me, and I'll tell you another guy that I normally do listen to.
Okay. Aubrey de Grey.
Oh, no.
Aubrey de Grey. Yeah, so he was doing, I think he was helping his girlfriend. He was working on the computer systems of his girlfriend's research lab, as in she was doing a PhD, I think, and this was in Cambridge University. And he did so much really cool stuff with the computers that they gave him a PhD. He didn't write a thesis or anything. And then it was just really weird. So since then he's been like studying gerontology, aging. Yeah, he's got this like, I think, yeah, he's a British guy, long hair, long beard, and graying, I think. And he says that I think there are like 7 things to stop aging, and he uses the analogy of like a car. So you can replace bits and you can stop the rust forming, and you can, yeah, I don't know, you can clear out stuff and you can improve things, and you can stop mutations. Yeah, so that's interesting. Yeah, who have you been talking about?
Yeah, I was. I normally have heard of this guy, David Sinclair. He's called.
David Sinclair.
Yeah, and
Okay.
he seems to be also a pioneer in this field when it comes to longevity and other discoveries regarding how to expand the lifespan. And initially started, if I'm not wrong, his studies with mice and yeast, doing tests and experiments with them. And there are some practices, if I say, that can be applied to, well, us humans, of course, that would help us, let's say, age slower by taking some. He has given some actually not medicaments, because he's mostly a scientist, but he takes himself some sort of chemical supplements that help him, of course, stay younger. And apparently, he seems to me as well. It's well and healthy, and doing well for his age, let's say, because he's 50 and he looks really good. But anyway, so that's one guy that I've heard, and I normally do listen when it comes to advancements in healthcare. There are some other guys that call themselves that work, well, do this biohacking, but that's pretty much trying to take different approaches of how to keep ourselves healthier, eating, for example, good foods, doing some intermittent fasting, for example, some tips for that they would say, or I don't know, even taking cold showers, because they seem to also boost the immune system and things like
I
that.
heard of that.
But this is kind of pretty much the biohacking community. So they have some approaches or some kind of lifestyles that they are following in order to stay at the top, of course, of their health for themselves. In addition to guys like David Sinclair, which they are doing research and trying to bring some medicine, let's say, or advance enough the medicine field to treat also aging with, not necessarily with these lifestyles, but also with a pill, shall I say. Let's make it a magic pill now that you take, and
Yes, please.
of course you get some years back.
That would be great.
Yeah, definitely, because we expect, of course, to see much more in the future, and it's really, I think, kind of an exciting time, of course, to be alive, because well, as human beings, thus far, we've never been, I think, much safer. And also we're seeing the progress getting steeper, like the progress curve of technology, I think, steeper and steeper, which means that we're gonna have it even more difficult to predict what's the next thing, let alone several years or decades.
We need AI models to help us.
Yeah.
Yeah.
But
So like you mentioned CRISPR, and I thought about that before. Like, if so there's some error, and it can cause its mutations itself. Like when you say, I want to change this bit of DNA, engineer the CRISPR to do that. Palindromic repeats. Anyway, so you do that, but then it kind of might change a few other things. And then there was the question, is this going to cause a whole load of mutations in people? And then I think the answer was, it doesn't seem to be too bad. But then, like aging, I think it's copy errors in your cells basically build up, and then stuff doesn't work like it's supposed to, like it does when you're a kid. So yeah, if you could use CRISPR to say there's been some mutations or some copy errors there, just put them back. Like if you took a survey of thousands of cells, millions from all over the body, and you could vote on what is the correct gene or the correct letter of the DNA in that position. That's probably how reading your genome works. And then if you could do that, then you look at the various cells and you find there are things that are not the same as that pattern. Then you could correct them with CRISPR. But hopefully it wouldn't then give you other mutations. And actually there are newer technologies. So CRISPR doesn't work on non-dividing cells, but I forget the name. Something does. So like, I think the heart and the eyes, they don't really grow. They don't have cells dividing all the time. So CRISPR doesn't really work. But somebody, maybe 2018, 2019, found something, developed a technology very similar to CRISPR that it does work on non-dividing cells as well. So you could do that. But then I guess aging could be less of a problem, or even more. I'm not sure.
Yeah, definitely. There are a lot of questions actually that arise from these, facts or aspects. If we see that there are some treatments or some techniques to treat some types of diseases, in this case, the mutations that are created in our bodies due to cells not dividing efficiently or losing information while dividing. And of course, you mentioned a good point, which I also believe. Yeah, with CRISPR, you might not know exactly if you added a segment or you replace a given, let's say, letter, in our genetic code, what would be the consequence of that longer term? Exactly, you cannot tell, because our bodies are complex machines. And in my opinion, it would be, I think, difficult to say 100% is going to be safe, but at least it is a mechanism, maybe those simple tissues that you can sort of fix and repair. Maybe there should be a combination of most tools somehow to give a radical approach or complete, let's say, regeneration of our bodies. So that's
a combination of what?
A combination of different methods, maybe not only CRISPR, I would think, but also the gene and stem cell therapy, where you inject, those stem cells to kind of reboot the cells of that particular organ, be it skin cells or liver cells or heart cells, or even the eye, because you raised a good point. Eyes do not really grow. Okay, they might kind of slightly change, but over the years they do not really grow in size. That's a fact that we should be aware that since we were born, our eyes pretty much have the same size. That's interesting.
Yeah.
But Vincent, if I apologize, I just see a notification. I need to go meet someone quickly. Of course, I would wanted to have a discussion even long because these topics are interesting. But yeah, how about maybe another time we also, have a conversation about these things?
Oh yeah.